Okay, think for a moment about the car you drive, right?
Yeah.
Or maybe vital medical devices, industrial controls, even defense systems. They're all running on embedded systems, working quietly in the background, real unsung heroes, powering our world. So today we're doing a deep dive into something really critical, but honestly often overlooked: embedded software security. It's all about making sure these systems, which are everywhere, are resilient against, well, growing threats. We got some fascinating insights here, especially from the Strength in Embedded Software Security by RunSafe Security. They lay out a pretty specific way to tackle this, our mission, to pull out the key nuggets, help you understand how to proactively secure these systems, scalably, uniquely, without messing up performance or slowing things down. All right, let's start unpacking this. Why are these embedded systems, which seem so efficient, maybe even isolated, why are they becoming such a huge target now?
Well, it's the sheer ubiquity. It's kind of amazing when you think about it. Medical devices, aerospace, industrial controls, automotive ECUs, those electronic brains in cars, they are, literally everywhere. And the material we looked at, it highlights that attackers are really focusing on the software inside firmware, bootloaders, OS kernels, middleware. So the big question is why? Why are they so vulnerable? Often it's because they just lack basic runtime protections, memory safety controls. And if you step back, this isn't just some technical glitch, right? It's really a frontline issue. We're talking national security, critical infrastructure, the integrity of devices we use every single day.
Okay, so if they're everywhere and vulnerable, what does that mean for the code itself? The source material really points a finger at C and C++ llama.
Exactly. Those languages, let's be honest, they're notoriously memory unsafe. We see these memory safety vulnerabilities like buffer overflows, use after free errors popping up all the time. And these aren't small bugs. No, these are critical flaws. They can be used for remote code execution, all sorts of malicious actions.
What about the traditional defenses then? Things like ASLR, address space layout randomization, or stack canaries, do they actually help?
They do offer some protection, sure, but the sources are clear. They're not foolproof. With enough determination, attackers can often bypass them, which really just highlights the need for something more fundamental, a proactive defense.
Right. Okay, this is where it gets really interesting, I think. The research talks about a method that goes right to the root cause.
Yeah.
Hardening the software at the binary level. How does that work? How does it change the game?
It's a really significant shift. The core idea using tech like RunSafe Protect is to randomize the binaries when they're built, build time. They use techniques like Load-time Function Randomization, LFR. So imagine this. Instead of just trying to detect an attack that's already happening, this approach makes it way harder for attackers to even exploit memory flaws in the first place. Why? Because the code structure is constantly shifting in memory. It's like dynamically rearranging where everything is located each time the software runs. Makes those predictable attack chains basically impossible.
Huh. So it's like shuffling a deck of cards every time the hacker tries to make a move. They're like, cheat sheet is useless.
Yeah. Precisely. Yeah, that's a good way to put it. The deep dive explains it breaks exploit chains. And critically, you don't need to change the original source code. This means it can stop whole classes of attacks before they even get near the device. And importantly, it works without adding runtime overhead or requiring source code access. So it neutralizes known bugs, yes, but also unknown zero-day threats. How? By eliminating entire classes of memory safety flaws. And those flaws, the analysis states, are the root cause of nearly 70% of embedded system vulnerabilities. 70%.
Wow, 70%. That's huge.
It is. It means you're tackling the biggest attack vector head on. You end up with every binary image being functionally identical but logically unique.
Okay, so beyond hardening the code itself, the sources really emphasize SBOMs, software bills of materials. They call them table stakes. What does that mean exactly? And why aren't all SBOMs the same quality?
Right, table stakes basically means they're essential now, non-negotiable, foundational. But like you said, the quality can be all over the place. Many traditional SBOM tools, well, they often miss key dependencies. Or they generate a lot of false positives, false negatives. That makes them less reliable for actual security work.
So how do we fix that? How do we make SBOMs more accurate and genuinely useful for security teams?
Well, the proposed solution is to enhance how they're generated, build them during compilation. The idea is to report on every file opened during the build process. This creates what they call rich and accurate SBOMs, especially for C and C++ code running on Linux, Windows, even RTOS environments, those real-time operating systems.
So are SBOMs just about ticking a compliance box then? Because you hear about regulators pushing for them?
That's a fair question. And yes, regulators are pushing. UN R155 for cars, FDA for medical devices, the DoD has requirements. But the research really stresses they are much more than that. They're your first line of defense in software security.
Hmm.
They give you real visibility into your software's risk. They show you, okay, what third-party libraries might be risky, and importantly, where vulnerabilities could spread across systems.
Okay, this next point. It feels like a massive headache for so many industries.
Mm.
Legacy systems.
Mm.
How do you possibly secure something that's ancient? Maybe the source code is gone, the tools are outdated, patching is a nightmare.
Oh, yeah. You've definitely hit on one of the biggest, most persistent challenges in cybersecurity. It's huge. And yet these old systems, they're still running critical infrastructure, defense platforms, life-saving medical devices, keeping them secure when you maybe can't patch them in the traditional way. That's incredibly tough.
So what's the practical solution here? What does the source suggest for that kind of, well, nightmare scenario?
This is exactly where that Run Safe Protect technology is positioned. It's built for this exact scenario. The idea is it disrupts cyber exploits by relocating software functions in memory each time software is run. So it effectively neutralizes, they claim, 100% of memory safety vulnerabilities, keeping the system intact. And the key part, it does not require access to source code or changes to the original software.
No source code changes.
Yeah.
That's huge for legacy stuff.
Absolutely vital, especially for sectors with those really long product life cycles, strict recertification rules, think aerospace, defense, industrial control, medical devices. Imagine securing a system that's maybe 20 years old without having to recompile or rewrite anything. That's the promise.
It really sounds like we're moving beyond just building higher walls. The material talks about cyber resilience versus just relying on perimeter protections. What's the philosophical difference there?
Yeah, that's a good way to frame it. If you look at the bigger picture, traditional embedded security often focused on the outside. Firewalls, secure boot, encrypted communication, strong perimeters. But the problem is, once an attacker gets past that initial wall, systems are often left wide open. Lateral movement, privilege escalation, remote code execution all become possible.
Okay, so what's the paradigm shift then? What's the resilient approach?
The shift is towards embedding advanced cyber resilience directly into the device itself. And again, this points back to that load-time function randomization, the LFR tech. By relocating software functions in memory each time the software runs, it makes attacks fundamentally unpredictable and unreliable. It disrupts memory-based exploits, things like buffer overflows, return-oriented programming, ROP attacks, even if vulnerabilities exist in the code.
Even if the bug is still there.
Exactly, because the exploit can't reliably find its target. So it shrinks the attack surface and really hardens the system from the inside out. It's kind of like assuming a breach might happen eventually and building internal strength to withstand it.
Got it. Okay, finally, the research pushes for making security part of the build process itself, not bolting it on later. What does make security a build-time discipline actually mean for, say, developers day to day?
It means integrating security smoothly, almost invisibly, into the existing DevOps pipelines, the build processes developers already use. The platform described automates things like vulnerability identification, authoritative SBOM generation, and patented memory relocation. It hardens the software at build time. So the main idea is to let engineers keep focusing on what they do best, building features, improving performance, while the security stuff just kind of happens behind the scenes, proactive security, but without disrupting the workflow.
Okay, this whole deep dive has really shown us a sophisticated, multi-layered approach to embedded software security. Who is this most relevant for, and what's the big picture impact?
Right, that brings us to a key point. Who really benefits most? Where does this apply? The deep dive lists several areas. Industries like automotive, defense and aerospace, energy, high-tech manufacturing, industrial automation, medical devices, even railway. And specific use cases, well, application security hardening, CI/CD security, cloud workload protection, DevSecOps. Also securing embedded devices themselves, mission-critical assets, OTIS devices, that's operational technology, industrial control systems, and strengthening the software supply chain. Think concrete examples like military systems, advanced driver assistance systems in cars, those ECUs we mentioned, and meeting FDA compliance for medical devices.
And who inside those organizations needs to be paying attention?
Good question. It's relevant for product leaders, certainly developers and engineers, industrial asset owners, and definitely the product security teams.
So, for you listening, what's the ultimate takeaway here? What's the smarter path forward for securing these embedded systems?
I think it boils down to making your systems fundamentally more difficult to exploit right from the start, by design. The tools and the philosophy we've discussed, they aim to stop those memory-based attacks cold. They aim to generate high-quality, truly actionable SBOMs right at build time, to secure legacy code without those painful, expensive rewrites, to embed resilience deep inside the runtime environment, and to shift security left in the development cycle. All of this, ideally, without breaking builds or slowing delivery. The ultimate goal, to deliver code that's harder to hack and easier to trust.
That was a really insightful look into this complex but absolutely critical world of embedded software security. It's pretty clear that securing these systems isn't just about chasing down individual bugs anymore. It's about a fundamentally different approach: proactive, resilient. So as we wrap up, here's something provocative for you to think about. If solutions exist that can neutralize whole classes of vulnerabilities, like that massive 70% coming from memory safety flaws, and can secure even tough legacy systems without rewrites, how might that change the entire calculation? For maintaining critical infrastructure, for managing devices with super long life cycles, especially facing constantly evolving cyber threats. What else could your teams focus on if that burden was lifted?